Hey everyone, this is Mayur. Welcome to ML Works. In this video, we'll talk about regularization in machine learning. So, in machine learning, we often see when we train a machine learning model, the model tries to perform well on training data set, and when we put it in production, or even when we test it on test data set or an unseen data set, the model's performance drastically worsens. Now, the reason for that could be the model is overfitted on your training data set and it fails to understand the unseen data. Now, this could be can be a problem because we have a data set which is simple and we try to apply a complex model on top of it, which leads to overfitting of the model on a particular data set, which is training data set in this case. Now, to avoid this, what we can do is we can apply regularization such that we can avoid this hard understanding of features with labels and such that the model is generalized for unseen data as well. Now, there are a bunch of approaches that is available for regularization, and some of the widely are L1 and L2 regularization. Now in L1 regularization, what it tries to do is it tries to drop the features, some of the features by turning some of the parameters into zero. Okay, such that we are totally removing some of the features from your data set and we are trying to map the other features with your label. Okay, that's how L1 regularization works. And in a sense, what it does is we have lambda here along with your loss function, a general loss function. Then we apply something called as a penalty, which is plus lambda of summation into all the summation of all the parameters. Okay, so that's the L1 regularization, which is absolute value of your parameters. And there is also other approach, which is L2 regularization, also known as ridge regression or L2 norm. Okay, what it does is instead of turning the parameters into zero, it turns them into a smaller value. Okay, such that some of the features will have smaller influence on your mapping between features and labels. Okay, so that's what L2 regularization does. It doesn't remove the whole feature in a sense as L1 does, but it tries to reduce the influence of some features. Now let's look into the implementation aspect of regularization. So what we'll do is we have a house price prediction data set, which is a Boston data set, and then we load the models, or then we import train test split. So we import that and then we segregate into features and targets or labels as called, and then we segregate into train test where training is around 80% of the records are under training and 20% under test. Now we can look at number of features that are present currently. There are 506 records and there are 13 features present. Now we'll start with lasso. Okay, then we'll look into ridge and then we'll look into linear regression. So initially what we'll do is we'll apply that. Since here it is mentioned as lambda, it is also in sklearn it is termed as alpha. That is the penalty we are applying on your parameters. Okay, one is a smaller penalty. Okay, once we apply this, when we are defining lasso as alpha is equal to 1 and lasso dot fit, then we do after fitting the model, then we test the model on the test data set. Here it is performing, it is giving around a mean accuracy of 66.7. Okay, and what happens in the backend is it tries to turn some of the features to zero. Okay, that is what is happening in the backend. We'll do the same here, ridge also. Okay, and here if we see the score is 66.6. Okay, so if we look at both of their coefficients for now, lasso dot coefficient. Okay, there are only 3 features are dropped. Okay, and majority of the features are retained in this case. In ridge we have all the features, but their value will be quite smaller and their influence will be less, and that's why we see a smaller difference in mean accuracy when compared against each. Okay, that's the reason. Now what we'll do is we'll apply the same thing using linear regression. We define, we fit, then we score the model. So we get an accuracy of mean accuracy of 66.8. So among these three, Okay, only this performs better by a small margin of zero point 0.1. Okay, that is basically why it happens is because we are trying to impact each feature individually by with the help of this lambda into these parameters. Okay, that's why we see the difference in the results. Now what we'll do is we'll test it out against a different set of penalty score like 5, and then we'll see the performance of these models. They're giving higher penalty, which means more number of features will be dropped, and which will directly impact the performance. Okay, we can see for alpha is equal to 5, the lasso ridge provided a score of 55.8. Okay, and if we do it on ridge regression, alpha is equal to 5. We don't see much change in performance, a small drop maybe, because there is much more value or smaller, the parameters are reduced by little more. Okay, that's why the performance also little dropped by 0.666 to 662. Okay, so that is the thing, and we can look at since we have increased the lambda or alpha value, the more features are dropped. Now we can look at the coefficient of each of these models. Okay, this is for linear regression. Here we don't drop any parameters or features, and if we look into lasso, if we see here we have 1 2 3 4, then again 4. There are totally out of 13, 8 features are dropped and just 4 or 5 features are used to do the prediction. Okay, so that is what lasso does, and what ridge does is tries to reduce the parameters value and such that it can reduce the influence of features on the labels. So here again, if we see, all features are 0.03, 0.01. Majority of the features have less than 0.0 value. Okay, so majority of the features have smaller influence on the label. Okay, now if I change this into 20, penalty to 15, let's turn it into 15. So we keep seeing the performance keeps dropping. Okay, but we don't see much change in ridge, and it will remain same for linear regression. And if we look at lasso's new coefficients, okay, there were 8 earlier, now it is 9, and other features also have much more lesser value. Okay, 0.007, 0.001, 0.01, 0.4. So all the features have lesser what influence on the label. And if we do it for rich, okay, again it doesn't change much actually. It is we have to keep track of each of those values to understand this better. Okay, so the point that I want to make is from this particular notebook is that when you have a model, okay, which is overfit to a simple data set, then you can apply regularization such that you can drop some of those features which are tightly labeling your modeling your data set and your labels. Okay, so you can avoid that using loss function with penalty using L1 regularization or L2 regularization. Okay, with this I'll conclude this video. I hope you understood what regularization is and how you can use it in your machine learning tasks. Thank you.